Solar energy offers a viable solution to our growing energy need. The solar panels can be so cheap and so efficient that the whole city could be powered by sunlight. While adoption of conventional solar panels on rooftops has grown rapidly in the last decade, there is still plenty of opportunities for expansion. The inspiration is to make solar cells transparent. Someday, the entire surface area of a building's windows could be used to generate electricity, and you will be able to see through them, allowing many of the surfaces of our built environment to be turned into solar harvesting arrays without impacting the function or the aesthetics.
The secret behind the transparency of the new solar cells is the range of absorbency. While range of absorption of the conventional photovoltaic cell overlaps significantly with the visible light, the transparent cells absorb all energy from the sun except the wavelengths of the visible spectrum.
Alright, I get that, but if it's transparent, how does it still work? And what is it made of?
In order to achieve such a specific spectrum of absorption, the researchers drew on the inherent characteristics of some organic materials, such as chloroaluminium phthalocyanine and carbon-60. These materials have an excitonic property, in other words, are semiconductors. Chloroaluminium phthalocyanine is an electron donor, while carbon-60 is an electron acceptor that shows peak absorbency in the UV and near-infrared spectrum. So, we have a pair of semiconductors who are only active in the near-infrared and ultraviolet, but besides that work the same way as the doped silicon layers. This active layer is sandwiched by two layers of indium tin oxide, an electrically conductive and transparent material. ITO plays the role of cathode and anode in the structure and connects to the external circuit which carries the current out of the device. A layer of distributed Bragg reflector plays the role of a transparent near-infrared mirror, reflecting the IR light back for a second pass into the active layer. An anti-reflection coating is added at both sides of the glass. Finally, the thickest part of the structure is the transparent substrate, which can be any rigid or flexible transparent material such as glass, plastic, quartz, etc.
The generation of electricity begins when the light strikes the solar panel and transforms the energy from photons to moving electrons in the electric field. The electrons are then guided to the edge of the panel, where very thin stripes of solar cells convert them to current and can be attached to the outlets. The efficiency of transparent cells is currently around 5%, but is realistically expected to reach 12%, which would make it comparable to the efficiency of conventional solar cells that range between 12 and 16%.
Only by stacking the transparent cells one on top of the other, 10% efficiency can be achieved, while maintaining transparency. If we try to make opaque solar cells more transparent, the only way would be segmenting them or thinning them, and by consequence reducing their efficiency down to 1% for only 10 to 35% of visibility. The transparency of the transparent solar collector is on the other hand above 70%, which is in the range of tinted glass used in windows of buildings and automobiles.
The advantages include controlling glare and reducing thermal gain inside a building. It also cuts down air conditioning needs and offsets the total energy consumption. Also, they have the ability to turn everyday products such as windows and electronic devices into power generators without altering how they look or function. So we can say that the cumulative efficiency could by far exceed that of opaque PV cells whose usage is only limited to solar fields and rooftops.
It is estimated that 1/2 to 2/3 of cost of the conventional solar cells comes from installation, glass, and structure of the panel. But since the transparent film does not require neither glass nor structure, its cost is greatly reduced down to that of energy-saving films that are currently applied on skyscrapers. According to the researchers, this technology looks very promising in Silicon Valley, California, where it was developed, and we decided to see if the technology could be applicable here in Montreal. We chose the highest building in Montreal, Le Mille de la Gauchetière, and we calculated that with a cross area of insulation of around 16,000 meters squared, it would generate 1,160,000 kilowatt-hour per year. The payback time of the installation will be 26.9 to 86 years, assuming 5% efficiency. For a single residential window, the heat loss would be reduced by 6.5%, and the payback time would be 9.5 to 30.4 years.
We conclude that the transparent solar cells are definitely a think outside the box innovation. However, at its current efficiency and cost, it is best suited for hotter and sunnier climates, where the buildings spend a lot more money on air conditioning and don't want the infrared light to penetrate through the windows.